All right, let's take a look at section 3.3. Now, what 3.3 does is piggyback off of the idea that when you are doing a sample of a population, that sample is giving you again just a best guess, an estimate at what might be true concerning the population, maybe what their average is, maybe what their proportion is. Now, what we did in 3.2 was say, well, let's expand that out to do an interval to be a bit more transparent. Our sample is only given as a guess. We could be off. Whatever the parameter is, it might actually be as low as this, it might be as high as that. But in order to create a confidence interval, one of the things that you need is a standard error. And the only way that you can ever get a standard error is if you do more than one sample. Actually, what we're going to be saying is that we need to do many samples. The problem with that, though, is that for some researchers, whenever they do a study, it might have taken them a month just to do one sample. So they would need to do a second month and a third month if they wanted to get more samples, and for some, maybe even a year, maybe even a decade to do their one sample. So in that situation, what do you do when you've only got one sample? In that situation, you won't be able to do a confidence interval to say, hey, here's where the parameter is contained, maybe as low as this, as high as that. However, the good news is that someone came up with a method known as the bootstrap method. And what it does is it creates, I know, same word again, it's going to generate bootstrap samples. Now, what this looks like is that, again, suppose that you have done a sample. And again, I'm just to keep the illustration on the small side right now. Suppose you have done a sample and it took you a month, right? And you got your six individuals, and either it was something about like their height, and you got each of their heights, and you're like, oh my goodness, I would like to do a confidence interval, but I can't because I only have one sample. And you're thinking, well, I'm going to need to spend another month to get my second sample. But the bootstrap method, what it does is it will create for you a second sample that's inspired by that original sample. And so what it'll do is whenever you have your original sample, well, there they are. It's going to treat them as if though they're the population that you can be selecting from. And so what it'll do is, it'll reach in and maybe it'll grab that person as as the first selection, but then it'll put them back. And then maybe it'll grab that person as the second selection. But then because you put them back, it resets so that you might end up picking that person a second time again or whatever value they possessed. And you continue to go to where you might end up selecting this person in the bottom corner like two times. And then, of course, you would end by selecting your, oops, got rid of all my words. Then you would end up stopping once your bootstrap sample is the same size as the original one. And just like that, lightning fast, you have a another sample and you saved yourself a month. Now, it's not just about saving time. It's about the idea that when you do this method, it actually shows that it's gives you very good results. So here I'm gonna keep going and just bear with me. You're gonna be like, wait, this feels like kind of like cheating. Again, why would somebody do this method? The main thing is that if you only have one original sample, you have standard deviation, but you don't have standard error. And again, just let me pause for a quick second. Standard deviation is whenever you have one sample, and in that one sample, you might have, let's say, 10 people. Well, the standard deviation is going to be how much do those individuals in that one sample deviate from each other? Like how different are their values? But in order to do a confidence interval, you need not just one sample, you need a whole bunch of them. And so what the Bootstrap sample will do is it'll pull from that original sample and create a bootstrap. And it'll pull from that sample again and create another bootstrap. And it'll pull from that sample again and make another bootstrap. As many as you want, 10, 100, 1,000 of them. And that's the way that you can mimic the idea of actually going out and doing a second, a third sample, a fourth sample, but you're not actually really doing it. You're just letting them get inspired by the original. And once you've done 1,000 of these, you'll have the variation that exists amongst those samples and have a standard error. And if you're thinking, wait, the standard error, what was the standard error? The standard error, remember what we were doing in 3.2 is we were doing confidence intervals and you needed your statistic and you needed to do a minus version and a plus version of 2 times your standard error to get your lower amount to your higher amount, like the range of plausible values. And again, if you don't have a standard error, you won't be able to do that. But again, someone came up with the bootstrap method. And sort of like the big punchline to this is like, well, why not actually go out and just really do it? Why do it this way where you're faking like you did it? Well, again, because there's some researchers who maybe their study took 10 years. And so they'd have to do another 10 years to get their second sample. And what I'm going to put right here is the word impossible, right? For some researchers, it's not going to be possible. It's not going to be feasible for them to actually really go out with their own blood, sweat, and tears to get a second sample. That's okay. They can bootstrap it. And what's crazy is that if somebody was to maybe do a comparison, like let's say I went out and I actually did it. I did, you know, a month, 2 months, 3 months, 4 months, 6 months of like getting 10 samples. And you, on the other hand, you just went to StatKey with your one original sample and you told it to do 10 samples just lightning fast. And we were to compare like the results that we had, they'd be so similar. Like maybe I would come up with a standard error point like 0.023 and you'd come up with 0.024. They're like, oh my goodness, only a difference of like a thousandth of a degree. I mean, of a decimal. Like that's not a big deal. And so yeah, they have shown that this method actually works really really well. Um, but there is some, hey, you got to be careful when you're doing this thing. Again, what it's doing is it is selecting values from the original sample. And so I think the first thing to get this method to have any sort of legitimacy is that whatever that original sample is, I mean, you're putting a lot of hope into that thing that those individuals that you collect the data from are not biased. So, in other words, we're really hoping that original sample would be a random sample, or I think the better word there is that it's unbiased. That sample is a good representation of the population. And if it is, then it's okay to select from it as if though it were the population. Now there's a few more rules, or at least two big major rules whenever you're doing the bootstrap. If your original sample is deemed to be the unbiased sample, then its values are the only ones that you can select from. Like it's the golden sample. Now, as I showed you a moment ago, duplicates can happen. And that's because whenever you're doing the bootstrap method, as you select the values, they are being replaced. So we'll say replacement is used. And so what that does is increase the chances that you're going to get duplicates, which is a good thing. Because if you didn't do replacement, you would just get the first person, the second person, the third, the fourth, the fifth, the sixth, and you'd get the exact same original sample every single time. So by putting them back, you're allowing for more spontaneity, for more who knows what you're going to get, right? Sort of like by randomness. Now, the other thing is that whenever you create a bootstrap sample, every time you create one of the rules is that it must be the same size as the original. And so here I'm going to show you an example. And usually, if I had like my in-person class, I would have them help me come up with some values. But since it's just me doing the recording right now, and if I were to ask you, hey, let's suppose we were to go do a study about the average amount of TV that students are watching, and our original sample is going to have 8 different values in it, and let's say it takes us maybe a month to go out and do this. And the first person, again, just in your own head, you could think of some numbers. Like what might students say is how much TV that they're watching, per week. And someone might say, well, I do 10 hours. Someone might say, I do 5. Someone might be like, oh, no, just only like 1 hour. I'm not a big TV person. Then you got some that are like, well, I watch 25, right? I'm crazy. I love TV. Someone might do like 40, and then and so on, so on. So again, I'm just coming up with some numbers that might be values that we get a an original sample of just 8 students, and there we go. That took us a month. Now, what the Bootstrap sample does, or what the Bootstrap method does, is it'll start now generating for you new samples inspired by those values. Now, rule number one is that each of the bootstraps have to be the same size. So if the original one had 8 numbers, so does each bootstrap sample. The other big thing is that whenever you select the value, you can only select what's available in the original. So when we do this, and I want you to maybe even try it on your own if you could, is that where you select one, like even get like little pieces of paper, right? And get all 8 of them, write them on little pieces of paper, and like pull one out, see what you get, and then mix them all up and put that one back, and then mix them all up and pull out a second one, and then mix them and put it, write that number down. So let's suppose I did that, and I were to get like 20, all right, and then I put it back and I mix them all up, and I pick out something random. I might get like the 25, put it back. And I want you to try this, right? Like just with like 8 pieces of paper, like put these numbers down, and you'll see that you should not get the exact same thing back. And suppose I put back my 25, mix them all up, and I get the one. Mix them all up, put that one back, and then suppose oh, hey, I might get the 20 again, and just keep going, right? Put that back. Maybe you get the one again. Mix them all, put it back, mix them all up. Maybe I get the 10, put it back, mix them all up. 18, put them all back, put it back, and then mix them all up, and then you get, boom, maybe the 40. And so that's a very good possibility that something like that happens, where you get some of the numbers that show up more than once, um, duplicates, and then you do it again, right? And again, yeah, and again, I encourage you to try maybe getting, just 8 pieces of paper and putting the original numbers, and as you select one, record it, put it back, mix them up. Do a second one, record it, put it back, mix them up, and just keep going. And so again, another thing that could happen is maybe the second time around we get like the 18, and we get the 25, and the 5 and the 10, and for a little bit you might be like, ooh, it looks like I'm gonna get the whole same thing back again, but then boom, the 18 shows up again, the 5, the 40, and the 1. And again, that's another possibility of what could happen. Is it possible that you select exactly just one of each of them? Like you get this guy, and then you get this guy, and then yeah, it could happen, but very unlikely. There's more of a chance that you're going to get something like this to happen, like a 5, and then put it back, and then you get the 20, put it back, and mix them up, and you get an 18, put it back, and maybe the 5 again, where you end up starting to see like duplicates happening. Now, I'm not actually really doing it right now with my 8 pieces of paper, but usually I have my students do that, and they'll see that, yeah, every time that we're doing that, it's usually like some new version of the original sample, but not the identical original sample. And just like that, we saved ourselves a month. another month, and another month. But again, it's not just about trying to save time. They have shown that this method, when you do it, you get these nice variations of different samples, and the standard error that you get from it is very similar to if someone actually really went and did with their own blood, sweat, and tears and walked around and did another sample and walked out and did another sample and put all the actual time into it. And just to go ahead and just reiterate like the rules to the bootstrapping, because that's similar to the one we just did, is that if this is our original sample and it's got five numbers, then you can look down here, A, B, C, and D, like which one of them is already breaking one of the cardinal rules regarding size. I'm sure you already see it. It's right there. It's the very first one. That would that would be something that we would say no to. And the question being like which one of these might be a possible bootstrap sample? Nope, not that one. And just give it a short little reason why, right? It only has four values. Explain why not. It only has four data values. The original one had five. And you don't exactly have to say it like that. You could have also said no, it needs to have five numbers, or no, it doesn't match the size of the original sample. And then there's also another one that should be a no. Now the original, the only numbers available were 8, 4, 11, 3, and 7. So look at the other three, B, C, and D. Which one of them is breaking the rule about not only being able to use values from the original? I'm sure after just a little bit you'll see it. It's right here. That guy's the bad guy. And so all you would say is you would say no on the homework, and then you would explain why, like what the issue is. And notice that five is not something that you would have been able to obtain from the original. So you can say no, five is not an original value. And you don't have to even be that specific. You don't have to specifically say five. You can say, has a value that's not an original value. But usually, what most students would do is specifically call out what is the number that's the bad guy or the imposter. So the two that are left are both possible. Yeah, these could happen. Yes, it is possible that when you reach into the original sample that you get a 4 and you put it back, mix them up, get an 11, put it back, like again, because replacement is used. So you put the 11 back, you mix them up, and you get a 4 again. And then you put that back, and then boom, you get a 3, and you get another 3 back to back. So that could happen. And it's got five numbers like the original. And then D is the one that I wanted to kind of save for the last little piece before we go on, is it possible that when you reach into the original sample that you get a 7? Yes. You put it back. And then whenever you mix them up, you pull out an 8. Yes. And then you put it back. You mix them up, and that you happen to get the 11. Yes. And you put it back. Then you get the 3. You put it back. You mix them up, and you get a 4, so that you get one of everybody. Yes, that could happen. Probably not very often. But the reason why I have that one there and it's a yes is because you could have selected each of those numbers. Yes, maybe one of each. It's got the right size. It's got five numbers. It doesn't have any duplicates, but that's okay. Notice that what the bullet point up here says about duplicates, it says replacement is used, meaning you put the pieces back each time that you select another one, that duplicates are likely to happen, right? So if they don't happen, that's not to say that something's wrong. Now, in terms of like doing the bootstrap and actually let's use it for the purposes of getting a standard error. Again, remember the main goal here is that we want many samples. And when we do that, that's where we get our standard error. And again, if you're not totally sure about this method, they say that it can be a great way to estimate your, a way to create your confidence intervals. And we'll be doing more with this as we go on. But today, the main thing is to be able to do confidence intervals. And again, a lot of this rests on things being done in a randomized manner, and the distribution when we walk away will still at the center have the best estimate for the population. And what I want to do here is now show you like how will we actually really be going about getting uh, 1,000 of these samples. And it's going to be Stacky who's going to be helping us with this. Now, the example that I have here is one about hockey, and it's the average amount of minutes that players, whenever they commit a break a rule or a violation or a foul, that they get put into the penalty box, right? For doing something they shouldn't have done. And there's actually only one sample that they did for this, and if that's all that they have, they won't have a standard error. But we can bootstrap it. We can create a bunch of samples from that, and from there achieve our standard error. So here's what we're going to do. We're going to go to a place that we haven't gone yet. It's the bootstrap confidence intervals, and there's different versions of it. Some where you're trying to do a mean, some where you're trying to do proportions. So I'm going to go there with you, and what we're going to do is just make a note of what the shape of the graph is, what's the center value, and then the biggest thing is what's our standard error? How much are the samples different from each other? So it's Ottawa Senators, fourth edition, penalty minutes, 2024. So I'm going to come here and open up for me a new tab. Oh, I don't need that. I need this. Go into Stat Key. And once you get to the homepage of Stat Key, right here in the middle is what we're going to be using for Chapter 3 bootstrapping. And you can see the very top one is the one that includes doing something about a mean. So you'll click on that one. And then go to the drop down and find the Ottawa Senators. And again, fourth edition, 2024 penalty minutes. And right up here in the corner, you can see the original sample. It was 23 hockey players that they did. And the mean was 35, about 35, almost 36 minutes on average that are being spent in the penalty box. Now, right now, this one sample has standard deviation. Like how much do these values for these 23 players like differ from each other? But with that, that's not the same thing as standard error. Standard error is whenever you have a bunch of samples. And right now we've just got this one. So in order to create our standard error, right there is where you can generate 1,000 of them. And so what it did is it pulled values from the original sample. And watch here, I'll do this real quick. Right, if you click on the show data table, this is the original. This is the original sample of players, the 20 some odd players that they did. And so now what Stacky did to create these 1,000, and you can click on some of those. Like if you click on maybe, you know, whatever you have like to the far right, or I mean, any of them. And for each of your bootstrap samples, it'll show you that it selected 23 values from the original. Watch, I'm going to click on my little show data table for just one of my bootstraps. And you can see here that these are the values that it's, and look at that 134. That 134 for me is the idea that when it's selected values from the original, like it got that 134 not just once, twice, three times, four times, and put it back, and that's why it showed up more than once. But again, it's following the rules and that it's selecting only values from this original. And since the original had 23, each bootstrap also has 23. All right, so that's just a little side, little comments that I have. But the main thing here is that we've got a graph that's got roughly symmetric and bell shaped. It's got a tail to the left, tail to the right. The center is 35.723, which yours might be a little bit different than mine, but pretty close to like 35, 36, which is what the original sample had estimated. And then the great thing is now we have a standard error. And so give me just a quick moment. I'm going to write these down so that I can put them on my lecture handout. I've got in here. Take a little side note for myself. But go ahead and start writing yours down. Yeah, we've got right there. I've got 35.723 as my center. 35.723. And then your standard error should also be similar to mine, like 5.943. So if yours is a little bit different, that's okay. Again, because this is all about things being done in a randomized manner. And so let's go ahead and go over to our lecture handout and record these. Because then what we would do with them, we're not going to do it for this example, but we would use the standard error to be able to create our confidence interval. You know, the initial estimate was that maybe about 35, 36 minutes or how long they spend in the penalty box. But then we could say it's as low as this or as high as this. And we'll do it in just a moment. Symmetric, bell shaped. Now, we're not going to do it on this one, which is that we do the the plus minus two times. Like we'll say that we're going to do it in just a second. What I want to do on this one is just mainly focus that it's stack key. That is what can be used to do the bootstrapping. Now stack key can also give us what the interval is, and notice the two blanks that I have at the bottom. That's what I want to do. I want to just to show you real quick that stack key doesn't stop just at doing the standard error. That if you wanted it to give you what's the plausible range of values, there is these three little boxes, and you can click on the one that says two tail, and right there at the bottom is it's giving you the plausible range. Like, how long do players in the hockey league spend in the penalty box? And again, yours will be similar to mine, but not exactly. I've got 25.348 as the low, and I've got 48.826. And so you would take that and you would put that on one, put it in your lecture handout, but then also keep in mind you're going to do something like this in the homework. And so whenever you're done with your homework problem, you would take a screenshot of this and make sure to include it with whatever your answers are, and make sure that you show at the bottom, hey, here's my interval. I'm going to go to put mine. So what we're walking away with is that the average amount of time that, and hold on, I got to real quick to check my number. 348. Yeah, 348. So players might be spending somewhere between about 25-ish to about 48, almost like 49 minutes on average in the penalty box. Okay. So that's how we get standard error. That's how Stacky does the bootstrapping. And that's one way that we might have Stacky give us a confidence interval. And here, let me just real quick mention like how did Stacky get that? What it did, literally did, is it counted 95% of the middle dots that are from the center. And so this is where it's saying these are probably like your guesses that are too not good guesses. And these are also your other guesses that are not too good. But the ones in the middle that are the black dots are, 95% of them that have pretty reasonable guesses. All right. Well, let's keep going. Let's try something else just to kind of keep grooving and moving along with this. And it, again, for some students, this is some of the stuff that's more conceptual. It does take some time for it to grow on you. But here's one that's already done. So when I say what I mean by it's already done is that it's already been bootstrapped. And so right here, this was a study in 2010 where they asked individuals, do you believe or agree that there's solid evidence of global warming? Now, when they did it, they actually only did it once, which is the one that's there in my screen. They talked to 2,251 people, and 1,328 of them said that yes, they felt that there is strong evidence for global warming, which would be 59%. Now, with that alone, they would not be able to do a confidence interval. But the good news is that they were able to bootstrap it, and you can see that they did it 3,000 times and created all of these dots. Now, once you have this, then you have your standard error. Now, this is a graphic that I'm using from the authors, and this is actually incorrect. This should be SE. This is the standard error. 0.010 is the standard error. That's how much all these samples deviate from each other. So things that we could do once we have one of these graphs, first we could talk about like what's the best estimate, which is going to be whatever's at the center. So maybe it's about 0.59 or 59% of individuals at that time believed those strong evidence for global warming. Now, to do whether this is a P or a P hat is important because they're asking for the notation. But there should be something there that gives you a hint why this should have a hat on it. So because they refer to it as being the statistic, that's when you would use a p hat because the idea of like bringing it back to the sample. Now, because they bootstrapped it, we have many samples. Now we have a standard error, which is right here, the 0.01. And we will use that to build our interval. So again, you're going to take, here's a little side note. You're going to take your statistic. You're going to do a minus version, a plus version, 2 times your SE. And remember last time we talked about how with your, if it's margin of error, you don't have to do times 2. But whenever you're doing standard error, yes, you do need to double it. So these are the two things that you would put into your calculator to get how low of a value it might actually really be, or how high of a value the proportion might really be of those who said or agree that there's strong evidence for global warming. You should get 0.57 to 0.61. And I often just leave them as decimals. If you prefer switching those to like 57%, 61%, even like with my answer key, most of the time I just leave it as decimals. But If you're more of a percentage person, then definitely go for it. Um, I'll take your answer either way, as long as whenever you do switch it to percent, you do it correctly. Um, now, if you have your notes from the last section, 3.2, I gave on there a template. I'm going to go ahead and just reiterate it here. Whenever you're asked to interpret a interval, like to talk about this thing, there are some key things you must include in that interpretation. Which one of those things is this, which is the level of confidence. We are 95% confident that and then here's where you got to mention, what was the study about? Was it about mean? Was it about a proportion? Was it about a difference between two groups? Since this one was about percentages, proportions, we put proportion. And then you talk about who was the study about, and they mentioned it up there. It's about Americans. But I'd say it's probably not a bad idea to just go to interject the idea that the study was intended to try to say something about all Americans, not just about the 2,000 people who actually were surveyed. I mean, they if they could have, they would have liked to go and ask every single American, but Plan B can't go ask everybody. There's just way too many people out there. It's just to do a sample. But yeah, the big takeaway is about all Americans, and then now do the variable. This was who say. But yeah, if you have a moment, you can totally like pause this video and just real quick grab your lecture notes from 3.2, and on one of those pages when we were doing the interpretations of intervals, I kind of had in there all the stuff that you want to make sure to mention. So the one that I'm writing right now is the variable, who said that there's strong evidence for global warming. And then the last thing is between where and where. It's something between 0.57 and 0.61. Again, if you want to switch it to percentages, you can. But again, you'll notice often that on my answer key, I usually just leave things as decimals. And the reason why is because a lot of times with the decimals, we're working with those more often when we're doing like divisions and we're doing multiplications and additions and subtractions. A lot of those are in decimal form. All right, let's take a look at actually just one more problem. And again, the cool thing about this is that a lot of times, right? This is the big takeaway of what 3.3 is all about. Is that if you were to do a study and you were to base it off of just a sample of people and you get your estimate, that's all you've got. You would not be able to be transparent and let your audience know that, hey, here's my estimate, but I could be off. It could be as low or as high as this. But thankfully for the bootstrap, you'd be able to bootstrap it and create your confidence interval. Now, what I'm doing with this one is it's doing a hey, what if actually just kind of putting it all together. Yeah, this one is putting it all together. The study was about teens, and I'll just put a circle around it. All right, this one here was about a proportion that when they talked to a sample of 920 teens, 644 said that, yeah, anxiety, depression, those are a big deal, right? They're a big major issue that they're having to deal with in life. And that right there is the original sample, but with that alone, you wouldn't be able to do part where's it at? Part B. Yeah, you wouldn't be able to do part B to be able to do the lower, the higher, like it goes from here to here, because you don't have a standard error. You would do statistic plus minus two times your standard error. You're like, oh my goodness, I don't have a standard error. But that's okay. What you're going to do is we're going to go here. We're going to go to the bootstrap stuff. We're going to go to single proportion, We're going to find the study that has the sample about the teen problem, anxiety, depression, and we're going to bootstrap it 1,000 times. So I don't think we need this one anymore. Nope, we don't need it. We're going to go to right here, bootstrap, single proportion. Right here, you're going to go and you should be able to scroll down. Thankfully, they have them in alphabetical order where you got teen problem, anxiety slash depression. And you'll see that's what they mentioned. They found out that 70% said that anxiety, depression are like a big issue, a big concern. You'll see right here, we have no standard error. But the moment that you bootstrap it 1,000 times, go ahead and do it. Now your standard error shows up. Notice that it's also it's roughly symmetric bell shape. I mean, maybe there's a slight little bit of skewing one way or the other, like maybe to the left some, but I'd say roughly symmetric bell shape. The center of the interval is going to be zero point 0.7. And if you got something a little bit different there, like 0.699 or 0.701, that's okay. And then same thing here, the standard error, you're going to want to write that down. And I've got 0.015, but if you've got something like 0.014 or 16, that's okay. This is the one on the homework. I mentioned it last time in the last lecture is that if when you go to the answer key and because of the randomizing that's happening, if your answer versus like the answer key is just like a hair off, right? Or just a few decimals off, that is okay, right? Do not count that as being wrong. Again, I got my answer just by the randomness. So there's no reason to say like my answer is better than yours, right? It's just we're randomly doing these things. But I'm going to go to write both of those right over here. Shape wise, is that it was symmetric and bell shaped, point 0.7. Now, if you ever have like point 0.7 and like extra zeros after it, you don't need these. Yeah, you don't need these two extra zeros. And then boom, right there. That's the thing we needed. We needed that standard error. So now when we do the statistic, and again, I recommend that you do the minus version first and the addition version second. That way it already kind of flows out in order from left to right. And these are ones that I already calculated ahead of time, but if and that's only because I got the same numbers I got the last time I did this. If they change or if they're different a little bit for you, I got 0.67. And again, if you got something slightly different, that's okay. Again, they're just estimates. Now, what I want to do real quick, the last one of the last things we need to do here is like write the interpretation for this one. But before we do that, I just want to do this last little part here. This is us doing it manually with the formula, but Stacky doesn't do it that way. Stacky does it where it counts the middle 95% of the dots. Like if this is the distribution, it counts how many are 95% of them in the middle. And that's how it gets its cutoff of like the lower to the higher. So let's do it. Let's just compare ours. Here's mine 6773. And then what we're going to do is hopefully you still have your graph there to get its way of doing the 95% interval is you would click on the little two tail. And so it's not doing a formula. What it's doing is it's literally counting 95% of the middle dots. You can see mine's got point 672 and 0.732. So very similar. Actually, one of the numbers is exactly what I got, but No, it's not. Not. Yeah, they're both close. Yeah, 6-7 and 7-3-2. But I'm gonna go to write those. And here it'd be better to show you just on my lecture handout. But let's see if I can remember those. 672.672. And let me see what my other one was. Down at the bottom. Yeah. And that's where you're gonna get yours from too. I got 0.672 and I got 0.732. Point. So not the same as what I have up here, but pretty close. I mean, they're only off by like 2,000th of a decimal, and that ain't gonna hurt anything. But again, the reason why they're different is because we're doing like a more formula based calculation, and Stacky's doing a literally counting all 95% of the middle dots, which is still the idea of trying to do like two deviations from the center, left and right. Now, to end this, we're gonna just do a our final little interpretation. Again, you have to start off with the level of confidence. We're 95% confident. The and actually let me have you just give this a shot on your own and use the example that we did earlier about global warming and see if you can just and you can, right? I'm just gonna give you a chance to do it. I don't want to like steal your thunder. Yeah, just use the one that we did in the last example about uh, the proportion of those who said there's an issue, there's strong evidence for global warming, but now just match it to this new problem. Again, go to like pause the video if you need to do that and give it a shot. Now I'm gonna go ahead and do it for myself as well, and then maybe once you're done, you can compare and look back over here. And all right, there we go. So again, the main things that you want to be really detailed with these. So I'm gonna underline the main ingredients. You want to put the level of confidence, whether it's about a proportion or whether it's about a mean, who the study was about. Again, I don't think this is a bad idea to include that this was about the entire population. And then you want to have your interval. I went ahead and switched it to percentages. Again, I'm totally flexible whether you leave it as just decimals or whether you switch it to percentages. And you also don't have to use the word proportion. Instead, you could switch it to percentage. But then the other parts that I didn't underline is the variable. The variable is whether they agreed that anxiety, depression are a major issue. All right, so that takes us to gets us to 3.3. The next one is going to be 3.4, but I'm going to go ahead and end the recording there.